Hello, welcome to a new lesson to study the Legendre Polynomials. Today we are going to look to an integral representation of the n-order Legendre Polynomial. Okay, so we are going to remember that the definition of the n-order Legendre Polynomial is p sub n of z equals to 1 divided by 2 to the n factorial. And then we are going to take the n derivative with respect to z of z squared minus 1 to the n. And I'm using z because in this video we are going to think that z is a complex number of the form a plus bi. Okay, and we are going to define the function f of z as 1 divided by 2 to the n factorial times z squared minus 1 to the n. In this case, we see that if we take n derivatives with respect to z of this function, we are going to get p sub n of z, right? So we will get that f to the n of z is equal to p sub n of z. Of course, this notation is to remark that I'm taking the n derivative of the function. Okay, perfect. So we are going to make use of a very famous formula that is from Cauchy, that comes from the Cauchy theorem. Okay, so we are going to establish that the n derivative of a function f is going to be equal to n factorial divided by 2 pi I and the contour integral of f of u divided by u minus z to the n plus 1 du. Okay, well, this is a very famous relation that comes from the Cauchy's theorem. Okay, and we need to remark that for this to hold, f of z needs to be an analytic function, which means that, well, it is going to have an infinite number of derivatives. Okay, it is infinitely differentiable. Okay, perfect. So with this, we can write this integral in terms of the definition of f that we have here that corresponds to the Legendre polynomials, okay? We said that the n-order Legendre polynomial is equal to f to the n of z, which is going to be n factorial divided by 2 pi I, and then the contour integral of f evaluated at u. Okay, but that is going to be 1 divided by 2 to the n factorial, and then u squared minus 1 to the n. And then this is divided by u minus z to the n plus 1, and then du. Okay, perfect. So in order to find an integral representation of the Legendre polynomials, well, we need to solve this integral, right? Okay, so with this, we see easily that this n factorial can cancel with this, and we are able to write that p sub n of z is equal to 1 divided by 2 to the n, taking this out of the integral, and then 1 divided by 2 pi I, the contour integral of u squared minus 1 to the n, divided by u minus z to the n plus 1 du. Perfect, and this is something that is going to be known as the Schläfli formula. Okay, let me write it. Is Schläfli formula. Right, so this is already an important result, but it's not the elegant way that we want to find to express the Legendre polynomials in terms of an integral representation. Okay, so we still need to work a little bit more with this expression. So what are we going to do? We are going to define that the variable of integration is going to be on a circumference, right? That is going to be parametrized by, well, complex numbers, okay? This is using a change of variable as u equals z plus rho e to the I5. And why is this? Well, with this change of variable, we are saying that we are locating u on a circumference that is at the center z, right? Because remember that z is a point on the complex number of the form a plus bi, and then we are going to generate a circumference of radius rho that is going to be with the angle phi that parameterizes the circumference. and it goes, of course, from 0 to 2 pi. So it's like having in the complex number this point over here, which is the number z, and then the circumference of radius rho. Okay, perfect. So with this change of variable, we can construct a new integral that is going to be of the variable phi, and that integral is going to go from 0 to 2 pi. So instead of having a contour integral, we are going to have a regular integral that we usually solve. So what are we going to get? Well, if we have the u variable, we can calculate the du element as rho I e to the I phi d phi just by taking the derivative, right? So what happens if we want to calculate u squared? That will be z squared plus 2z rho e to the I phi plus rho squared e to the 2I phi. Okay, so if we subtract -1 on both sides, we will get something like this. And then we need to divide by u minus z on both sides. But what will be u minus z? Well, from here, we see that if we take this z to the left-hand side, we see that u minus z is equal to rho e to the I phi. So here we are going to divide by rho e to the I phi. So what is this going to be? Well, we're going to factor 1 divided by rho here, and this will be z squared e to the minus I phi. And then, actually, we can take this -1 over here to get e to the minus I phi as a common factor. I did that for this -1 that we have here, right? So then we will have plus 2z rho, and then plus, what are we going to get? It will be rho squared e to the I phi. Perfect, and here we close the brackets. Okay, but we need to notice that, well, these two elements are raised to the n power and to the n plus 1 power. So we still need to work a little bit with this. Okay, so this is equal to u squared minus 1 divided by u minus z. So first, we are going to raise these to the n power. So u squared minus 1 to the n, and then divided by u minus z to the n, is going to be 1 divided by rho to the n, and then all this raised to the n power, right? But recall that we need to find u squared minus 1 to the n divided by u minus z to the n times another u minus z here, right? To get the n plus 1 power element. So this is going to be this element over here and times 1 divided by u minus z. But again, if we go back here, we see that u minus z is rho e to the I phi. So we will get here rho e to the I phi. Okay, perfect. So with this, we can now construct our integral, right? So we will get that p sub n of z is equal to 1 divided by 2 to the n, 1 divided by 2 pi I, and then the integral from 0 to 2 pi of, well, this quantity that we have here. So let me copy. Okay, there it is. And then it is going to multiply du. But du is rho I e to the I phi d phi. So we write here rho I e to the I phi d phi. And then we see that this cancels with this rho cancels with this, and we have an I here that can cancel with this. So what are we going to get at the end? Well, this will be 1 divided by 2 to the n, 1 divided by 2 pi, the integral from 0 to 2 pi of this. But let me erase this, and then d phi. Okay, so with this, we can consider a trick that is going to be that if z is different from 1 and negative 1, we are going to take that rho is going to be the square root of z squared minus 1. Okay, so that means that this quantity that we have here can be seen as rho squared. Perfect. So p sub n of z is going to be 1 divided by 2 to the n, 1 divided by 2 pi, and then the integral from 0 to 2 pi of 1 divided by rho to the n, and then rho squared e to the minus I phi plus rho squared e to the I phi, and then plus 2z rho, then all these raised to the n power d phi. Okay, and pay some attention here because you need to notice that what happens if we take these 2 rho to the n inside this thing. Looking that they are raised to the n power, we can take these elements inside these parentheses, right? And then, well, this is going to become the next 1 divided by 2 pi, the integral from 0 to 2 pi, and we're going to factor this rho squared. It will be rho squared e to the minus I phi plus e to the I phi divided by 2 rho, and then plus z, all raised to the n power, and then d phi. Right, and recall that when we take these 2 rho inside these parentheses, we can cancel that with these 2 rho that we have here to get only z here. Perfect. So this is going to be 1 divided by 2 pi, the integral from 0 to 2 pi, and then we will have e to the I phi, e to the minus I phi, right? Plus e to the I phi divided by 2 plus z, and then raised to the n power. And here we have our rho, right? Recall that it is very known that this quantity that we have here can be seen as the cosine of phi, right? It's a very famous formula. Cosine of phi is equal to e to the minus I phi plus e to the I phi divided by 2, which is not very hard to show. So what are we going to get? This is going to be a 1 divided by 2 pi times the integral from 0 to 2 pi, and then rho cosine of phi plus z to the n, and I forgot a d phi here, d phi. Okay, perfect. So if we go back with the definition of rho that we made, we are going to get something known as the Laplace relation for Legendre polynomials. That is going to be 1 divided by 2 pi, the integral from 0 to 2 pi, of the square root of z squared minus 1 cosine of phi plus z to the n d phi. So this thing over here is already an integral representation of the Legendre polynomials. Remember, this is known as the Laplace relation for Legendre polynomials. Okay, and another way that is very known to represent this same equation is to evaluate the Legendre polynomial at cosine of theta. So this is going to be 1 divided by 2 pi, the integral from 0 to 2 pi of, well, we have a z, right? But z is equal to cosine of theta, and then plus the square root of cosine squared of theta minus 1 times cosine of phi raised to the n power d phi. So it's easy to see that this is equal to the sine of theta. So we will get that p sub n of cosine of theta is equal to 1 divided by 2 pi, the integral from 0 to 2 pi of a cosine of theta plus sine theta cosine of phi to the n power d phi. Perfect. So this can be seen as an additional representation of the Legendre polynomials, but now evaluated at the cosine of theta. That can also be very useful. So I think that this will be the two important results of the lesson. Recall, it's just another way to define the n-order Legendre polynomial, right? But now here in terms of an integral. Perfect. So I hope you enjoyed this lesson, and thank you so much for watching.